Okay, so today we're going to start introducing the second project, and I thought a good way of doing it, rather than me lecturing on some system call stuff, I came up with a program that I want you all to kind of pair up or triple up or just get in groups basically and pull this program apart and figure out what it does. Look into some man pages and things of that nature. So I've got this Gold Chase Part 2 up, and the project write-ups there is a PDF, but ignore that. You don't need to look at that at the moment. What I want you to focus on right now is this pipeandfork.cpp. So everyone should be able to get a copy of that and should be able to compile it and run it. And doesn't look like it does much, but there's all sorts of exciting things in here. So we'll do that for a while, and then we'll come back together and talk about it, and then we'll use that as a kind of a way of talking. A project tool will make a lot more sense once you understand this program. Okay, so go ahead and have it that, and we'll just bring it back together. I don't know how long it'll take. I'll just play it by ear. So tell me in broad strokes what the program does.
Forks off a child, duplicates, changes its standard in, standard out to the pipe created by MakeFIFO. So it's reading from the parent and then writes, or reading, yeah.
So there's a little bit more being done than, it's a little bit overkill. There's code here that I could delete and it'd still run the same way. Let's focus on this line for a minute. What are the different arguments here? What's the difference between the first argument and the second argument?
First one's the executable.
So this is the executable, and what's the second one? Which argument?
To word count.
Say that again?
To word count.
Well, what if I do this? Will that run?
No.
So what is that second argument?
That's just the name.
You're on the right track. What do you mean the name? Let me ask a different question. What's this third argument? This is actually, and this is a, where is it? It's just a character array, right? It's this, so let me do this. Come on. Right, that's all that is.
Isn't the second one just argv0?
Ah, there you go. So the first argument to this exec function is the application on disk that you want to load into main memory and execute. Everything else is just the argument, the argv array, right? Argv sub 0, argv sub 1.
So it doesn't really matter what that second argument is.
Say that again?
It doesn't really matter what that second argument is.
It depends. So let me quit out of this. Let me see. All right, so these two, let me redo them on their own. So this is showing that in user bin there are two entries. One is for EX, and based on the syntax coloring, you can look at the long listing. That's an executable program, but they've put another entry in user bin called view, and all it is a link to EX. So this is the exact same executable, but what's different between the two is argv sub 0. So as far as the question, does it make a difference, the answer to that is, well, it depends what the application programmer did. You can examine argv sub 0 and do something different depending on what's there. And in the case of EX and view, EX is just a line editor, which if it isn't going to let me do it from EX. There we go. Whenever you're in Vim, you do colon whatever. That's kind of EX stuff that you're doing there. So that's why I started looking at Vim. In days past, there are 4 or 5 different executables, all linked to the exact same one, which was, then it would have been VI. And if it was VI, that was your traditional editor. If it was EX, it was the same editor but without the visual, just a line editor. If it was View, it was a read-only version of VI, excuse me. And so the application would examine argv sub 0 and change its behavior depending on what that contained. All right. So that's why that's 2 separate things. So I should change this back. Input file name. And then finally, the 0 here, if you actually look at the man page for the exec functions, these are all variants of each other, and a distinguishing characteristic between this first argument is one of them is going to look in your environment variable path, looking for that executable. The other one you need to provide the absolute path name, and it won't look in your path variable. So you have that distinction between which one you choose here. And then let's see, where's my different version? So these, what you have to do is you have to build the argv subarray, and then you just provide a pointer to it. These, you basically provide all the arguments separately. And these are variable argument functions, just as you can have an arbitrary number of command line arguments to a program. If you're coding this up, you can have an arbitrary number of arguments to the function. There then needs to be a way for the code to know when you're done with function arguments, and that is by making sure that the very last function argument is 0. Right? And so that's why the 0 is being provided right here. If you were to build your own, then I would make this argv sub 0, I'd make this string argv sub 1, and then I would have to provide an argv sub 2, which would be 0. So you can't get around it. You got to provide the null some way. So what's being done here is that in a very simple situation, you could have some sort of text file, and on this exec here, I would just provide the name of that text file. But what is being done instead is the parent process is controlling the information that the child receives. And the child thinks it's just opening up a file and reading it, but what in fact it's doing is it's opening up a pipe. And so that's why the first thing this process does is creates the named pipe here, and it has this name. And then that's provided, so if I do a man on WC, right, that's the argument that's being provided. And so the WC ends up reading from the input file, and it doesn't read from standard in. If I don't provide this, and in fact I was going to ask you all to do this modification in a couple minutes, if you don't provide this, then WC reads from standard in. So I can say WC, I can do WC on this program, and that'll give me a count of the lines, words, and characters in that file. Or if I just do that, then it's all coming from standard in. Then we get that information. So we go ahead and we do the fork, we do the exec, the child. First thing this child's going to do is try to open up this file. It'll open it up, but then it's going to stall because it's trying to suck input out of it, and there is no input yet to grab. So meanwhile, in the parent, and what is relevant, I don't know if, let me see. The write to child is not used at all. I don't think. No, you see. So this is what's redundant, all this write to child stuff. So write to child here, this, and then this right here is not being used. So none of that's being used. The only thing that's being used is the read from child. What does pipe do? It opens up a pipe, and it ends up being, it literally, when we're accustomed to doing something like ls pipe into grep a dot out, something like that, right? This pipe that we use at the bash prompt literally ends up, if you were to crack open the source code to bash, it would actually do this. So this creates, actually was playing with, trying to figure out how to bend X diagram to my will, not too successfully. So it literally creates this where, what do I want? I want that to, and then I'm going to do one of these, and then let me zoom in a little bit. Right, so the pipe command creates that, which is pretty useless. But what it does is it opens up two file descriptors. There's a file descriptor that is output, and there's a file descriptor that is input. And whatever you write goes into this read. So where it becomes useful then is when you do a fork. So note that both of these are done prior to the fork. Here's the fork right after it. So the fork creates two processes. So now we have the parent and the child. And what happens when you fork off a child is that it inherits all of the open file descriptors of the parent. In the very simplistic, I mean, you just have to think about it in the simplistic case of standard out. If you're doing cout statements and then you do a fork, and then both the parent and child are doing cout statements, both the parent and child are sending information to the screen, right? Because they're sharing the exact same file descriptor since it was copied. So to represent that diagrammatically, let me try this.
The cylinder represents the process, not the pipe.
No, it represents the pipe, not the process. The process will be this box I didn't draw around this one, and the box I didn't draw around this one. Whoever.
So, I think I'm misunderstanding. It looks like there's two pipes generated.
Because of the fork.
So there are two pipes? I thought they were both drawn from the same pipe. And that's what makes this.
So the pipe is a visualization of two file descriptors.
Okay.
One is an input file descriptor, one is an output file descriptor, and they feed each other. Or I should say the output of one feeds the input of the other, which is utterly useless for a single process, but brilliantly useful for, oops, oh, damn it, redo. Alright, so let me see. So this output is I love this book. Do that. Alright, that's what I want. Right? So this input descriptor was duplicated, and this output descriptor was duplicated. So this output not only goes here, but it goes here. Because these input descriptors are the same thing. Fork off a child and they're both going to C out, they're both going to the exact same place, yes? Okay, so it's the same thing here. I'm not done drawing arrows. I've got, how do I want to do this? It's going to go like that as well.
What do the arrows represent?
The flow of information from one file descriptor to the other.
Are there four?
Huh?
Are there 4 arrows now?
1, 2, 3, 4. Yes, there are.
You don't see how that could have produced 4 arrows. Oh, only 1.
There are 2 file descriptors there. Look at it's
Each arrow represents a file descriptor.
no. Each arrow represents a flow of information. There are 2 file. Well, there are 4 file. I guess there are 4 file descriptors and 4 arrows.
Each arrow is for 1 file descriptor.
Each arrow is flow of information. So what I can do, let me see if I do this and I do this. So now what I do is I start closing them. I close this one. Or let me see what would be, I guess I would close, maybe I'd do it here. If I close that, then actually let me close this one. Let me see, how do I, this is input, so output. I close that. That's going to kill that arrow, and that's going to kill that arrow, right? And then I close this. That's going to kill that arrow. Well, that'll kill that arrow. So what I'm left with is I'm left with, oh Christ. I just don't understand. All right, screw it. And it's going to wave. But the only thing that's left is if this parent writes to this file descriptor, this child will receive the information if it reads from this file descriptor. So a pipe allows you to create one-way communication. One pipe allows you, if you shut everything else off, allows, so where is it that I need? It is this one that shuts off. Where's my, there, do I have 3 now? 1, 2, 3, right, so this is the only, this descriptor hasn't been closed and this descriptor hasn't been closed. So anything I write out of here can be read from here, and this allows the child to read what the parent writes. If you want to go both directions, then what you have to do is you create a second pipe, And then when the fork happens, you close the other way around, and that allows the child to write and the parent to read.
What if you just don't close the other two files? What if you don't kill the arrows? Now you have two-way communication. Just use it with.
It won't work. It isn't two-way. It isn't. No, because
I mean, how we kill those arrows? If we leave those arrows.
then what'll happen is, so you don't even have to think in terms of fork. If I don't, let's look at just this parent, okay? And I've got this pipe, right? If I don't kill, it's not the arrows I'm killing, it's the descriptors I'm killing. So it's these big circles that cause the little circles to shut down, if that makes sense. When I kill this file descriptor, any communication to that is dead.
What if I don't kill those two file descriptors?
Then, okay, if I don't kill the two file descriptors, then I don't even have to look at fork. I can just look at the situation where I've done a pipe, right? I have the parent write to this file descriptor. Or I have the process. I'm not even talking about parents and children. I have this process write to this file descriptor. It blocks, meaning it hangs, because now it's waiting for it to be read on the other end. Well, it can't read because it's waiting to write. So now it's frozen. So that's why you have to close it.
Does the closing happen to the parent and the child? So those 4 close statements, is that the closing that we're talking about? I guess there's 8 of them.
Yeah, so note that for me to do one-way communication, the parent has to close one and the child has to close the complementary one. Yes? All right. So let's look at toChild. Here's toChild. Parent, and so we haven't talked about dupe yet, but dupe, in essence, the first thing it does is it does a duplication and then it closes. Oh, let me see. Is that the one I want? No, let me ignore it. Let me ignore the dupe, so we can ignore the dupe. So looking at this. All right, toChild. The child closes 0. See, it isn't working because I've done the duplications. Let me see if I can figure out how to articulate this, given that I've done the duplications. We have toChild. So what's being closed is toChild1 up here. This one, well, I can. The reason this one's being closed is because I did this dupe. So let me do this. If I get rid of that, then I'd have to get rid of this. And then down here, what am I looking at? toChild. So if I get rid of that, then I have to get rid of that. There. Now we've got toChild1 being closed here and toChild0 being closed in the parent. If I do my clever commenting out. Because I did the dupe, which I haven't talked about, I have additional closes in there. So I'm creating more open file descriptors that I have to deal with. So that is what's happening here, is for toChild, I'm closing what am I looking at? I'm closing 1 in the child and 0 in the parent, and then it's going to be the other way around. It's going to be 0 in the parent and 1 in the child for the other one to give me two-way communication. That said, we're not using two-way communication in this particular example code, so it's a little bit overkill. Yes?
For the sake of chase, are we basically like holding a pipe for every player playing?
You mean looking forward to what we're going to be doing?
Yeah.
We will, so we're going to be creating test code to test your program that you wrote for Project 1. And the way you'll do that is your testing program will be the parent, and then your parent will fork off children and execute your game and then test them. So it'll be using pipes to communicate back and forth. But we're working with incomplete information because I haven't finished. There's some other tweaks we have to do to make that work, but that'll be the idea. Is you have a big testing program and it's going to be firing off a couple players, making them do things, and then it'll end a test, and then it'll fork off another 2 game processes, and it'll test a bunch of different things in your game. And it won't be graphical at all. There will be no graphics to see. So that's what that does. Now let's talk about this dupe 2 for a minute. Let's actually look down here. This one's a little bit more interesting, I think. First, I would say that it's confusing to deal with these pipes as they're originally created. So these pipes are 2-element integer arrays, like on line 27 there. And it gets really confusing really fast, particularly when we get into the gold chase part and you've got 2 processes and you have 2 pipes per process. That's 4 pipes. So you can imagine 4 pipes with all this kind of stuff where you're like 2 parent from child 1, 0, 2 parent from child 1, 1, right? And then you just get a little glassy-eyed trying to stare at it. So what's being done here is I would just simply prefer to create a totally different file descriptor. I'm going to call it 20 because it's way up there. I don't have 20 files open, so I'm pretty safe. And then I'll make the last digit for me as a human to think, okay, 0 means input, 1 means output, just like standard in and standard out. So that's why I chose 20 and 21. So read from child 20, write to child 21. And then I do dupe 2, which what dupe 2 does is if these are open, it closes them, and they're not open, so there's nothing to close. And then it actually duplicates this file descriptor, so the writing to child is now going to be the same as 20, and the reading from the child is going to be this one. Now whenever I write to the child or read from the child, I can just refer to these file descriptors rather than these funky arrays. After I've done that, then I can close everything down, because to child 1 is exactly the same as write to child, so that's why I close this. It's redundant. I've got it from line 45, and then the same with the 2 parent. I can close that here. So, yes?
If we close it, if we duplicate that file descriptor before, and then we close the original file descriptor, the information is not lost. For example,
Nothing's lost.
If 2 child at 1 were open during that time, we open it into write. We transfer it into write to child, and it's opened. So that if we close the original file descriptor, the other one is still open.
That's right. They are duplicates. So if I can do dupe 2 15 different times, and then I can close 14 of the none of the 15 or all 14 of the 15, and I've always got anywhere from 1 to 15 file descriptors that do exactly the same thing. So what's being done here then is a little bit more of an interesting use of this dupe 2, which is, again, if it's open, it closes it, and definitely standard in is open, so it first closes 0 and then it reopens it as a duplicate of this pipe. And then the same on the right. So now, and this is how it actually, this is exactly what's done in the bash shell when you say ls pipe into grep. For grep, it does the fork, and then before it does the exec of grep, what it does is it shuts down 0 and it connects it to the pipe, right? So that it can read from the pipe when you're doing the traditional pipeline stuff. And then if you have a if you have a pipeline that goes with several executables, if there's one in the middle with a pipe here and a pipe here, then it's going to be grabbing input from one side and output's going to the other. So both file descriptor 0 on this end and file descriptor 1 on this end are being redirected to pipes, or being duped to pipes, using what we see on 34 and 35. So then we do the exec. WC just thinks it's running, doesn't know any better. It's going to, again, it's not using standard in because this has been provided. So it opens up the file, it reads in the file, then it wants to write the results to standard out once the file is read in. But we're in control of this. This isn't a file, this is our pipe, so it kind of hangs here waiting for that to open. So what we do is we open up, the parent opens up for writing to that pipe, and then it basically writes that entire string out in one fell swoop, this right here. Now, why am I doing that in this test program? Because you're going to do something like that in this auto test. Again, I don't have all the information for what that looks like, except to say you have your parent program and you want to test your game, so you fork off a child and you exec your game, and as the first player, right, you give whatever you call it, test prog or gold chase, and then that argument is the name of the map file, the text file. Well, you're in control of that now, and you're going to provide your name to a named pipe, and you're going to feed it a little test map through this pipe. And your game, the brilliant thing is your game doesn't know, just thinks it's opening up a text file. You just have to make sure the format's right. Send out an integer first, followed by a new line, and then the asterisks and spaces. So it's right. This is very important right here. If you don't close, then it won't stop reading. Let me closing these ends up not having a huge effect with this particular example. If I was to remove this argument here so that WC is reading from standard in and not from a file, then it's vitally important that you close everything in the parent that is writing to the child, because you want to know what happens if you don't close everything. Alright, WC, give me the results. Why isn't it giving me the results? Because what's still open? Standard in is still open, so WC isn't going to stop accepting input and doing its computation, right? If you don't close all of the inputs, it's just going to hang there, waiting for more information.
So is that what the end of file does? It actually closes standard in?
That's exactly what end of file is doing. So end of file is not, I'm going to now send a special character. It is literally closing that file descriptor, and then an error code, quote, error code is sent, which is EOF.
Okay.
So Control D is closing the file descriptor. And then once you, in this example, are closing it, now WC goes ahead and does its computations, and it immediately wants to spit the standard out. And I had to sit here and I ran a few examples. For instance, if I do WC etc hosts, whoops. I've got, why is this not? Well, that's interesting. I'm getting something different. I guess I was running this. Was I running this and got? So I'd have to figure out how to change. Let me see. What I don't understand is WC etc hosts. All right, so I've actually got different behavior here. I'm surprised that worked for me. WC etc hosts, WC Need something small. Yeah, you see what this is doing is it's spacing every. If you count this, there are 3 spaces here. So there's a field of 8, a field of 8, a field of 8. That's how I wrote this code. But it looks like the Vagrant version here is not doing it the exact same way. So I have a potential bug in my program. But that's what I was laboring under when I did this. I created the read is going to read literally 8 characters, so that assuming that I get output that looks like that, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, right? You get that kind of output. Then it's reading those characters. They aren't integers at this point, they're just characters. It reads them into this character array, then I do a conversion to an integer, and then likewise for the others to get characters, words, and lines. Then I just print them out, and I go ahead and close everything up, wait for the child to finish. Once the child is finished, then I go ahead and get rid of that named pipe that I created, that FIFO, in the file system. So, what I'd like you to do then is go ahead and read the project write-up, and then on Thursday we'll talk more about what needs to be done with that. Okay?